Well, thank you for that introduction, and we'll just wait while the thing goes up. Okay, well, thank you very much, everyone, for your attention, and I'd like to add my thanks to those that have been expressed all around, to the organisers and to everyone here. I mean, it's just an extraordinary meeting as far as I'm concerned, and I'm very honoured to be asked to speak to you. So my title, the exact meaning of what I have in mind with those words obviously will emerge as I go on. The placement of my talk should be, I think, seen in the context of the conference as a whole. It's not particularly applications, it's more fundamental physics. I intend to sort of be brave or foolish enough to walk a little line right on the edge of what physics we think is actually correct as far as our fundamental physics. Obviously, most of our study in science is new science, but it's applying fundamental ideas which we think are trustworthy. But of course, occasionally we're also interested to question those fundamental ideas. So I'll begin with a few comments on things that are not provable but reasonable. So that mathematics is consistent is an entirely reasonable thing to believe, but as anyone who knows a bit about formal logic, it's not possible to prove that from other axioms, although the mathematical community has done a good job of showing various ways in which you can increase one's confidence, but ultimately it's perfectly reasonable to hold that mathematics is consistent. It's also reasonable to believe that the classical complexity class P is not equal to NP, although that's, again, maybe one day that will be, we'll find out how to show such a thing. At the moment, very hard to see how one would prove that. But if I might quote from Maciek Levenstein from yesterday, every sane physicist thinks this is the case. And then my third one there, that classical computers cannot efficiently simulate every quantum system. Again, very plausible. I'll now add a few more. So that physical phenomena are indeterministic is something I'm going to talk about in a moment. That human reasoning can correctly arrive at some conclusions inaccessible to Turing machines. I think we should all feel somewhat more cautious about that, but nevertheless, it's a reasonable claim to make, and I'll say a bit more about that as well. If that were the case, then of course the next one would follow, that phenomena in the natural world cannot all be accurately modeled in algorithmic terms, because after all, we are ourselves phenomena in the natural world. And then the last one, I think is uncontroversial, but I think I want to highlight it, that there is scope for large amounts of new physics in correlated low-level effects. And that'll be what I come to at the end. Not clicking. I'm clicking away. Okay. So an outline. I will talk about a fallacy in logic, which I've named the Babel fallacy. Then I'll come to determinism. Then we'll look at finite state machines and algorithms. We'll move to quantum computing. I'll just say very briefly a bit about human behavior, and then what sort of thing could one conceivably say is going on in the natural world that's maybe not algorithmic in character. So the Babel fallacy, this is the name of a fallacy of the following type, of claiming that a given low-level grammar is capable of expressing a given high-level language when this has not been shown to be true. So first of all, that's a fallacious thing to do if you do it if you make a truth claim. It's perfectly valid to make as a conjecture that a fundamental grammar can express a certain language, but it will be improper to say that you know that to be true when it's not been shown. And I'll give you an example, or a few examples. So in economic modeling of the financial system, there occasionally have been economic models which claim to be capturing well enough what economic agents and how they behave. But of course, that is not all. That claim has sometimes been unfounded and indeed led to major financial trouble. So it's the degree of confidence one puts on the claim that the model you have is capable of expressing the phenomena you're wishing to look at. If we now go to linguistics, the Chomsky-Schutzenberger hierarchy is a well-known aspect of linguistic theory, and in that context, you can prove something like the Babel fallacy perfectly accurately. It's a sequence of languages, or grammars rather, and each step up the ladder of grammars can express more rich languages. So those that at one level simply cannot be expressed by grammars of a simpler kind. If we come now to logic and mathematics, I already alluded to the fact that mathematics has this rich character. But if we go back to the beginning of the 20th century, it was then proposed by many that one could capture mathematics more or less entirely by mechanical methods. We now know that to be not to be the case. So if a claim had that kind of been made very confidently, it would have been committing the fallacy I named Babel fallacy. Similarly, claims about the sort of all-powerful role of classical physics, which were made at the beginning of the 20th century, clearly were overclaiming. So one that you could make now would be to claim that algorithms, whether quantum or classical, can express all natural phenomena. The point is not to be too confident of that claim. It's a perfectly reasonable claim, and it's just that we really do not know it to be true. And then briefly on the name Babel, it comes because the name is apt because the ancient Hebrew story concerning the Tower of Babel was itself a reaction to pre-existing Sumerian stories in which the whole thought was that everyone will come to speak the same language, namely, obviously, the language of whoever wrote the story. And the Hebrews were saying, no, on the contrary, that will just lead to disaster, and we're going to have lots of languages. Anyway, that's just about the naming. Now, I've finished what I'm saying about that, but it will impact on what will come later in the talk. So now we're moving to determinism. So first of all, collisions in a gas. If you have the direction of motion of a particle in a gas inaccurate by a tiny amount, 10 to the minus 100 radians, then if you do a classical physics calculation, the spread or the uncertainty in the direction will become a radian after about 35 collisions, which takes about 7 nanoseconds. If you wait for a whole microsecond and you wish 1 radian precision, you will require to know the initial conditions to an accuracy of 10 to the minus, that's 14,300 radians. In order to know that, you would need to be able to place single atoms, need to know what the location was of single hydrogen atoms about 1 billion light years away back in the past light cone of planet Earth to a precision of about 1 angstrom. Okay, so of course that's not feasible to do that. Now, these facts do not in themselves imply determinism or not, but what they do show, okay, I'll come to the quantum treatment next. What these facts show us is that for many processes, it is not possible to confirm or disconfirm physical determinism by empirical means. So now the comment on the quantum calculation. So the classical calculation is clear. The quantum treatment, for a while I was quite unsure as to whether or not the sort of smoothness of quantum theory would somehow smooth away this type of exponential sensitivity. But there's a parameter called out-of-time order correlator introduced by Larkin and Ovchennikov in 1996, which itself has this character. You can calculate a Lyapunov exponent for that parameter for collisions, for example, in a Fermi gas, and you get pretty much the same value and qualitative behavior as was given in the classical calculation. I have to say, though, I'm not now claiming confidence that you can trust the calculation of that kind to the degree of, you know, the sort of precision of 1 part in 10 to the power of 14,000. I'm saying I really don't know. I don't know if there are hidden assumptions here, but it does appear to be entirely reasonable to say that even quantum physics is extremely sensitive in some of its behaviors to small effects. So nevertheless, this doesn't prove determinism or indeterminism. It simply proves that you can't tell empirically which may hold. So now we come to a claim which I think is a valuable contribution from Nicolas Gisin, who suggests this as a principle of finiteness of information density. The claim is, or the idea is, that a finite volume of space can only contain a finite amount of information. This is not something anyone can claim to know, and indeed it's not really there hidden away in the foundations of quantum theory. It's just a way of saying, well, this might be true of the natural world, and we don't know. But it's certainly a very reasonable sort of thing to say in view of what we've learned about information in the last 10, 20 years. And of course, it reminds us of work on black holes and if there is any relationship between information and energy, then of course a unbounded density of information would lead to an unbounded density of energy, which would indeed lead to a black hole. So again, this is not for certain knowledge, but it's a good way, I think, to think about what might be the case. In any case, if that is true, then in view of finiteness of information density and exponential divergence of trajectories or correlators, together those would imply indeterminism. And by the way, just in case you might like to know it, you can in fact build up classical physics entirely on this sort of foundation and have an indeterministic classical physics. So it's not true to say that classical physics is necessarily itself deterministic. It depends how you construct it. Okay, so a little bit more on the quantum case regarding these things. So quantum chaos, I already basically alluded to it. But the combination, again, of finiteness of information density and exponential divergence now of correlators in the quantum calculation together would imply the strict physical impossibility of observing quantum interference, for example, between a live and a dead cat. And I mean now, of course, an actual household cat, catus, or whatever is the Latin name. Nevertheless, the pure unitary method of calculation is still available. It's simply that it would now invoke unobservable quantities. That doesn't mean you shouldn't use it, but that's what would follow. The other thing I want to say about the quantum case, I'm just going to briefly wave my hands and remind you of Hawking radiation, Unruh radiation, and the black hole information problem. So the picture shows you a picture of Minkowski space with the four sort of regions that we commonly think about and that are often called the Rindler wedges. And then a statement of the vacuum state of quantum electrodynamics expressed in terms of modes of the right and left parts of such a expression of the vacuum. And of course, what we do in practice in order to calculate something like Unruh radiation or similar things for Hawking is that we trace over the degrees of freedom that lie behind a horizon. And that leads to a thermal state of the field. And what's remarkable there is that although the theory itself has every appearance of saying everything's unitary, and yet when you use it, you end up with things like mixed states. So there is this sort of subtlety, really, somewhere around pure quantum mechanics or possibly the interaction of quantum with gravity, which does seem to say that non-deterministic behavior seems to be naturally emerging from the theory. So again, this is just me sort of waving my hands a little bit at this stage, but giving you reasons to believe that it is indeed not provable but reasonable that physical phenomena are indeterministic. Now, finite state machines and algorithms, I'm mostly just going to remind you of some facts now. First, a real number is computable if there exists a Turing machine which, given n as input, terminates with the nth digit of that number as output. This is a definition of one way of saying, it's defining the word computable. Under that definition, the computable numbers are countable, whereas the reals are not. Every finite sequence of digits is the start of the decimal expression of an uncountable family of non-computable numbers. There exist numbers that cannot be approximated algorithmically. There are infinite sets of functions with no computable relationship to one another. So these observations about mathematics and formal logic do not in themselves imply anything about natural phenomena, but they show that outcomes not fully constrained by what went before might be expected. They also open our perception to the fact that algorithms cannot do everything that they might otherwise have been expected to do. Okay, so now I'm going to remind you of an argument often associated with Roger Penrose, but it also predates him to John Lucas, and it concerns human reasoning and the Gödelian proposition and the related halting problem in computer science. So I don't have time to sort of give you a starter course on all this. This part will only really be helpful to those that have some idea of what I'm talking about already. But the Gödelian proposition amounts to a careful construction of formal logic, which gives an outcome which is broadly equivalent to the statement, this statement is not provable within formal axiomatic system A. So if we just look at that assertion and use our reasoning and apply to it, we can quite quickly convince ourselves of the truth of that statement, that it's not provable within a given system. But of course, by the way the statement is formulated, the axiomatic system within which it was expressed cannot prove it. So Penrose and Lucas before him argued that this suggests the following, that it's as clear a demonstration as philosophy could reasonably hope for, that our arithmetical capacities, our human capacities, arithmetical in particular, and hence the powers of the human intellect in general, cannot in principle be simulated by a machine. But I want to also help you understand where things are now, because the broadly formal logic philosophical community did not suddenly decide, you know, we're not altogether convinced by this. The counter-arguments have been summarized helpfully by Wright in the following terms. Either no formal system encodes all information arithmetical capacity, the Lucas-Penrose thought, or any system which does has no axiomatic specification which human beings can comprehend. Okay, so either we are simply not capable of comprehending a full description of our own arithmetical capacities, or the processes in our brains, because we just could not grasp it all, or else indeed our thoughts exceed computational capacity of Turing machines. Okay, so again, this is where things stand. I thought people might want to have some idea of where it is. So we really don't know. So this, I think, the claim that our human capacities exceed what could be done in Turing machines is not provable, but it remains reasonable. I'm not saying that I'd necessarily, championing it, but it's a reasonable thing to suggest, and it's certainly suggestive for our further thinking. How am I doing for time? Okay, thanks. Now, a few thoughts on quantum computing. So a conjecture which I call here a 20th century conjecture is that classical Turing machines operating with physically possible resources. No, I do not say, I don't allow infinite. Physically possible resources, finite and not astronomically large. The conjecture would be that they could accurately calculate all physical phenomena. So that conjecture is very likely false. These things are not altogether provable, certainly in respect to which classical physics deals with those correlations which we call non-local. I think you can prove that it can't capture them. But when it deals with complexity classes, these things are not altogether provable. But in any case, that conjecture is likely false. But a 21st century conjecture might be a quantum computer operating with physically possible resources can accurately calculate all physical phenomena. Where I mean by a quantum computer, one equivalent to a set of quantum bits evolving by a sequence of logic operations, each of which affects a small number of quantum bits. Okay, it's a perfectly respectable conjecture, but I personally am not going to embrace it very tightly. There we are. I'm just going to leave it there. Certainly, I don't want to commit the Babel fallacy of making confident claims about it. Now, I remind you now of a fact about quantum computing, that it exploits entanglement as a communication and computational resource. I here just remind you of a very widely celebrated fact, which I would like to put to you in the following way. It's possible to find a two-spin state with the following properties, that if you operate on the state with an operator here called X subscript L for left, or else you could read London, you apply that operation, you will get a state orthogonal to the one you started with. You can apply an operation X subscript R, which you could read for right, or Rome. You apply that operation, and you will get a state orthogonal to the one you started with. And yet, when you apply both operations, the outcome is the very state you started with. The picture there shows you an ion trap experiment in the basement in Oxford run by David Lucas and Chris Balance, where precisely these things are done between ion traps separated by about a meter. And the point being, of course, that combination of properties on reflection really is quite astounding. it's the properties which go by, you know, we put words like local realism and non-locality. I want to say here that you don't necessarily need to think about the state and whether or not it's realistic. You can focus just on the observables. So you don't have to think about what happened to the quantum state. You can just note that various physical observables have these properties. My conclusion from that is that the attempt to describe the system as two separate parts is what fails, however you want to put words around that. And that's a sense in which reductionism, or the attempt to see the world, is entirely as constructed of separate parts and their interactions. That approach is not the whole truth about physical phenomena. Okay, now I think, I'm not sure about my time. Okay, this will be pretty quick. Let's define the phrase algorithmic paradigm in the sense in which the mathematicians have defined it for an effective mathematical procedure or mechanical procedure. It means a finite number of exact finite instructions that terminates, that is correct, that a human could do without aids, that requires only adherence to rules, not ingenuity. Okay, that's what the mathematicians, and broadly is what we all understand by this paradigm. Let's define FW to mean a freedom in certain complex physical systems. Humans would be a good example, but not the only one, perhaps. Anyway, a freedom to adjust their behavior on the basis of high-level considerations, or in other words, languages, which are not capable of being expressed by the algorithmic paradigm. Okay, so it's just a definition. You can't argue with it. I'm just inviting you to think about it. These things being so, you can make your choice of which syllogism to recommend. So the major premise here would be that AP implies not FW. If you make the minor premise AP is so, meaning I mean by that it's sufficient to describe all natural phenomena, you will conclude that FW is not the case. But I just want to say you can also reason this way. If you have as your major premise AP implies not FW, you could also introduce the premise not that FW is so, that there is such a freedom in certain complex physical systems, and you would conclude that algorithmic paradigm is not the whole truth about natural phenomena. Again, I don't think anyone should claim to know these things, but I want to keep people's alert to the fact that it's reasonable to hold either view. Okay, fine. So supposing the world were not entirely algorithmic, what else could be going on? The sort of thing it could be is, I mean, what is there room for? You know, what have we not already ruled out by, okay. Feedback from a whole to its parts with an influence on sensitive processes, perhaps especially on correlations. The impact of that would be swamped by noise in simple systems, but not necessarily in systems with sophisticated signal processing capability. So my idea is that I want you to think about the idea that there's plenty of room in these very fine sensitivities that exist in physical systems for new physics. This picture is a picture of a bunch of qubits subjected to noise, and supposing the noise is at the 1% level, and you have about 529 qubits encoding a 15-error correcting code, such as the Golay code and concatenated once, you will get a noise level at the level of 10 to the minus 12 for that part of noise which was uncorrelated. What will remain there is either, to all intents and purposes, noise-free, and you can then evolve the system at will and quantum compute. Or what will remain is whatever effects were not corrected away. You will thus have either outcome will be tremendous. You will either learn about new physics or you'll quantum compute, and I'd like to hope maybe both could be available. But I want to emphasize that this is really interesting territory, which I have to say we're not quite ready to explore, you know, in the next year or two, but it's not so very far away. So I have to conclude that. I apologize. Thank you, Donna, for allowing me to, I did go over time. I apologize. That last thought there reads, there is a vast and unexplored ocean of behavior of systems with non-linear behavior and signal processing. That's it. Thank you for your attention.